Okay, in this video, we will derive the Lorentz transformation. Lorentz transformation is important in the study of special theory of relativity and electrodynamics. And so first we have to talk about the difference between the special theory of relativity and the Newtonian mechanics. So Newtonian mechanics is based on the Galilean transformation, and in Galilean transformation, if a reference frame uh, S prime, which is moving with a speed v, with uniform speed v with respect to another reference frame, which is S, and suppose this S frame is at rest. So if you take any point P, which is at rest in the S prime frame, so let us take this coordinate with respect to S prime. Let us take this point P, and its coordinate with respect to S prime is X prime and Y prime, and in 3D Z. So for, in this calculation, we are only interested in the one-dimensional case. So we will just take one coordinate, which is X, and if you take its coordinate with respect to the S frame, and this will be X. So here this distance is X, and for any instant, let us take this S prime frame as traverse the distance Vt, and this distance is X prime. So from this picture we can say that the total distance X is equal to X prime plus Vt, and keep it in mind that in Galilean transformation, the spatial distance between 2 points and the temporal gap, the time interval between two events, is absolute. It is independent of any reference frame, so it is invariant everywhere. So if you take the time derivative of this equation, so this is dx dt, which indicates the speed of that point. If this point starts moving in x direction, so dx dt is the speed of that particle in S frame. So dx dt denotes the speed of that particle with respect to the S frame. And similarly, on the right hand side of the equation, the x prime also gets differentiated with respect to time. So this is dx prime dt, and this indicates the speed of that point with respect to the S prime frame. And third term, Vt, here V is constant because the S prime frame is moving with uniform speed, so this v will be as it is, and the time will differentiate it, resulting 1. So this is V. So from this picture, from this equation, we can say that the speed of the particle with respect to S prime is equal to the speed of that particle with respect to S prime plus speed of S prime reference frame with respect to the S. So here the velocity of that object is different in these two different reference frame. So the main concept in Galilean transformation is that the speed of anything, this is either a point particle or a system of particles or a light, so anything can have different velocity in different reference frame, but the time interval and the spatial distance between two points will be absolute everywhere, which is quite contradictory to the concept of special theory of relativity, because in special theory of relativity it is the speed of light which is invariant in every reference frame, but to keep the constancy of or the invariance of this speed of light, the spatial distance and the time interval can be different in different reference frame. So this is the main contradiction between Newtonian, the Galilean transformation, and the special theory of relativity. So with this thought in mind, we will now try to derive the Lorentz transformation for translational motion, and we will see the difference between these two transformations. So first we have to keep in mind that the time distance or the time interval or the spatial distance will be different in different reference frame. So in Lorentz transformation, let us take again a reference frame which is S, and let's say this is at rest, and another reference frame which is S prime, and that is moving with a uniform speed v with respect to the S prime. Okay, and now let us take the coordinate of any point P in the S prime reference frame, and here this is x prime, and because we have already mentioned that the time will be also different in different reference frames, so let us take t prime be the time which is observed from S prime reference frame, and let us take its coordinate x with respect to S, and the time is t which is observed from the S reference frame. And so we have already said that the speed of light will be same in every reference frame, so we can take a spatial distance x measured from the S reference frame, which is c multiplied by t, and this t is measured in the S reference frame, and in S prime reference frame x prime will be equal to simply c multiplied by t prime. Here t prime is measured from the S prime reference frame. So if you take the coordinates x, here x will be equal to x prime plus vt prime, and there will be a factor, and we have to find this factor with the condition that speed of light is same in this S and S prime reference frame. So if you want to take the inverse transformation, we'll just make the prime unprime and interchange the prime position and replace the plus sign with the minus. So here we can write x prime equals to, let's take this factor a will be same, and unprime this x and make the plus minus and vt. So this is the inverse transformation in Lorentz transformation, and here x prime equals to x, and again we can write the x as equal to x prime plus vt prime multiplied by a. So here x will be replaced by this equation, so this is a, and this will be x prime plus vt prime, and this is vt minus vt. Again we have seen that here x t is actually, from this equation we can write x equals to ct, so t is x by c. So in the next equation, in the next step, we can write x prime a x prime plus vt prime minus v, and just place the expression of t in this equation. So this is b and x by c. Again, we will rewrite this transformation here in this point. So x prime equals to a, this is a x prime plus v t prime minus v by c, and just put the expression of x from here. So this is a, again x prime plus v t prime okay. Now x prime, and let's take a and a from these two terms. Let's take a common. So this a and the a outside of the bracket gets multiplied, resulting a square. This is x prime plus v t prime minus v by c x prime plus b square c t prime. And now we can write this x prime equals to a square, and x prime remains the same, and v, and from this equation x prime equals to c t prime, and we can write t prime equals to x prime by c. So just put this expression here. This is x prime by c minus v by c x prime plus v square c, and again put this expression t prime equals to x prime by c. So this is x prime by c, and we can see that this plus and minus get cancelled out. So x prime equals to a square x prime, I'm sorry, this is not plus, this is minus. This will be minus this is minus, okay, x prime minus b square c square x prime, and from these two terms you can see that x prime is in common. So x prime equals to a square x prime 1 minus b square upon c square. So this x prime and x prime get cancelled out, resulting 1 in the left hand side of the equation. So a square is simply 1 upon 1 minus b square c square, and a equals to under root 1 minus b square upon c square. And so this is the factor a, and so the total result we can write. We have started from this equation that x equals to a x prime plus vt prime, and now x, put the value of, put the expression of a in this equation. So this is 1 minus b square by c square x prime plus vt prime, and b upon c is sometimes symbolized by beta. So you can write x is just 1 upon under root 1 minus beta square x prime plus v t prime, and further 1 upon 1 minus beta square is symbolized as gamma. So the final equation is gamma x prime plus v t prime. So this is the Lorentz transformation, which transforms the coordinates of x prime reference frame to S reference frame